Hello, and welcome to this lesson on problem solving using rational and irrational numbers. The central question says, how do I use rational and irrational numbers to solve problems? So fairly straightforward. So it can be a lot of word problems, problem solving, using these rational and irrational numbers. Did you know, without square roots, GPS could not exist? Like when you have your phone and it tells you where you're going and stuff. The way that GPS works is it works by finding the distance from you to 3 satellites in outer space. Some math is then done to calculate your position. It's finding that distance, and without square roots, we couldn't even find your distance because this is a distance formula. Now, the one that the GPS system uses is slightly different than this because this only uses X and Y. They would have one that uses X, Y, and Z, where the X1, Y1 would be your position in the X direction, and the Y1, Y2 would be your position in the Y direction. But look at this. You would have to do a square root in order to calculate the distance. So that's kind of cool, and that even applies into a lot of video games. If there's ever a game that says, like, you are this far away from a position, this is the distance formula that's going on in the background in that video game. There's no other way to calculate distance. That's used every time you need to calculate a distance from one place to another. That's how you do it. Okay? So that's kind of cool. This lesson, there is no new vocabulary because it's just kind of a rehash of old skills, but in a problem-solving format. So let's get to it. Example 1. It says here that the circumference of a circle can be found using the formula C equals 2 pi r. Sounds important. Where r is the radius and r is the radius of the circle. If the radius of a circle is a whole number, would the circumference ever be a rational number? So if the radius is a whole number, so we could imagine any whole number we want in there. 5 was the first one that popped in my head. If I plugged in a 5 here for the radius, would my circumference ever be a rational number? Well, let's see. If I would do this math in the calculator, let's just see what this gives us. 2 times pi times 5. That's very not helpful at all, calculator. The switcheroo button right above the enter button will make it more helpful. Now that's different than if we would have typed in 2 times 3.14 times 5. So 3.14 is that estimation of pi, and we get a slightly different answer. If you put in 3.14, a lot of people go, yeah, that's a rational number. That's a terminating decimal. It stops. Using the pi button, though, it doesn't stop. If you remember, pi is an irrational number. If we take that irrational number times by 2 and then times by 5, it's just going to be 10 times bigger of that irrational number. Every single digit is still going to be there. None of our decimal places went away. It's still bigger. So in this case, it would be irrational. Now I only thought of one example. I just used the number 5. Is there another whole number we could plug in there that would make this a rational number? I just thought of a tricky one. What about 0? If you have a circle with a radius of 0, which means you don't actually have a circle at all. So I think this is kind of a cheating answer. I don't think this really applies. But if you plugged in 0 here, 0 times pi times 2 would give us a circumference of 0, which technically is rational. I don't think that's what the question's implying, though. I think it wants an actual number like 1, 2, 3, 4, 5, like that. And the answer is going to be no. It's never going to be a rational number. Because no matter what you plug in here, I'll do something different than 5. 3. No matter what you plug in, pi is still going to be irrational, And when you take it times by these other values, it's still going to be irrational, just a bigger irrational number. So to answer the question, would the circumference ever be a rational number? Nope, it won't. It'll always be irrational. Letter B. Emily has a square with an area of 35 centimeters squared. All right, square area is 35 centimeters squared. And a cube. All right, cube. With a volume of 85 centimeters cubed. Which of these objects has the largest side length? So, sides of the square, sides of the cube. Which of these has the largest side length? So, background knowledge. Things we know. We know in order to find the area of a square, area is your length times your width. In this case, since it's a square, it would be like side times side, which is side squared, right? I know that the area is 35. It tells me right there, area is 35. Now, I could calculate this. I could solve this equation. Let's check this out. Because this is s squared, we learned in previous lessons that if I take the square root of both sides, the square root cancels out this square. Those are opposite operations. And we get just s equals. And then when I take the square root of 35, I'm going to get an irrational number, 5.916. Now, I'm going to round because we don't need to write every single one of those digits. I'm going to round it to 5.92. I'm rounding to the nearest hundredth. Now, if you remember, technically when you take the square root, you get a negative number as well, right? But I did say a lot of times we ignore the fact that a negative square root exists because it doesn't make sense. Like here, would it make sense if I have a square with a side length of negative 5.92? Have you ever seen a square with a negative side length? No, that doesn't make any sense. So in a lot of problems, we kind of ignore or drop the negative answer, but understand that it is there. All right, so square, that's how big each side is. And if I take my 5.92 times 5.92, I'm going to get something very, very, very close to 35. It's not exactly 35 because I rounded my decimal. Remember, I chopped off all those other decimal places? Now, for a cube, volume is calculated by doing length times width times height. Here, side times side times side, because all the sides are the same. That is the same as s cubed. Get it? It's a cube. It's the side cubed. It was a square. It's the sides squared. That's not a coincidence on why we call something to the third power cubed and something to the second power squared. This is why. It does tell me in the problem that the volume is 85. And now we can solve that problem. We have done that. That is an equation that we can square root. I can go, nope, I lied. Not square root, cube root. See the little 3 in the corner here? That's important. Cube root, because a cube root and a cube cancel. And I get just s equals. On the other side, when I cube root this 85, you could try to do this in your head, which we actually could do. We can estimate this, and I know this is going to be about 9 from that previous lesson, or using a calculator, 3 second caret 85. That's how you do cube root, 3 second caret. Oopsie. I did a square root of 85, not the cube root of 85. My bad. Cube root of 85 is 4.39. 4.39. If I round that to the nearest hundredth, the 6 makes the 9 go up to a 10, which makes this 4.4. So there we have it. My cube has side lengths of 4.4. My square has side lengths of 5.92. So then which object has the largest side length? I'm reading the question again. Well, the square has the largest side length. It's always good to use complete sentences when you can. There we go. Nice, pretty, perfect answer. The square has the largest side length, and there's all my work to go along with it. I think I'm going to do one more, and I think the next one will be for you. Mike was doing his math homework when his dog bit off part of the page, taking one of the expressions with it. Mike is trying to fix his homework and remembers that the missing expression was equal to 12 and looked like this. So this is equal to 12. What is the missing number from inside the square root that makes this expression equal 12? So we need to find x. Is really what this question is coming down to say. What is the x that makes this true? Okay, I'm going to rewrite the problem. 4 square root of x over the cube root of 27. So what I'm going to do is, my strategy, I could do guess and check. I could plug in 1 and then plug in 2 and 3 and 4 and 5 for x until I find the one that makes this equal 12. That might take a while, as guess and check normally does, but it could work. Instead, what I'm going to do is I'm going to simplify the problem as much as I can first. So I'm looking at the top of my expression here, this 4 square roots of x. I can't really simplify that. I mean, it's just 4 times the square root of x, and because I don't know what x is, I can't really simplify this. But the denominator of the fraction, I can. That's the cube root of 27. 3 second caret 27 should be 3, if my brain's working well today. There we go. So I've made the problem a little bit simpler. Now, I'm going to employ a different strategy now. Again, I can use guess and check. From here, if you're going in the forward method of solving this problem, that's the only thing we could do. There's a couple other things we could do. Maybe I'll show another method here when we're done. But the method I like to start working now from the end of the problem and working backwards. I'm going to start working backwards. So I know that this thing in the end needs to equal 12. Now I'm looking at this expression here. Eventually I'm going to divide by 3. So what would this top part need to be? So if I take this thing, divide by 3, I get 12. Something divide by 3 is 12. And that's 36. 36 divided by 3 is 12. And that 36 is going to be a 4 times by a something. 4 times by what is 36? 4 times, dig in your brain, 4 times 9 is 36. We are so close. We need one step in the middle. Oopsie. So now the last piece of the puzzle is, what do you take the square root of to get 9 as an answer? The square root of what is 9? It's not 3, if you're thinking that. Square root of 3 does not give you 9. It's not 9. It's 81. The square root of 81 is 9. So if this looked like that, the square root of 81 is 9. 9 times 4 is 36. 36 divided by 3 is 12. We kind of worked from the beginning of the problem a little bit, from the end of the problem a little bit, and we met back in the middle with our solution. So what is x? Well, in this problem, x equals 81. That's the method I like doing, but as I was going through this process, I thought of another way we could potentially do this, and I'm going to show you that right now. So I'm going to erase all of this. Pause it if you want to keep it. All right, it's gone. Now, I kept up to here because we still should simplify this bottom. I mean, this could easily be simplified to 3, and we should. But now what I'm going to do is I'm going to solve this equation. Let me make a new page here so I have space to work up and down. And I'm going to solve this equation because we know this stuff equals 12. Okay, so I'm using this equation in my head. So things we would do. If you wanted to solve this equation, I would start by multiplying by 3 on both sides to cancel out this divide by 3. Right? That we are allowed to do that. The opposite of multiply, or the opposite of dividing by 3 is a multiply by 3. These cancel. I have 4 square roots of x equals 36. That looks awfully familiar from what I had there a second ago before I erased it. I'm going to divide by 4 on both sides to cancel out that multiply by 4. Square root of x equals 9. We determined the same thing a little bit ago. And now, in order to get rid of this square root of x, do you remember what's the opposite of square rooting? It's squaring. If I square both sides of the problem, which we're allowed to do because we did it on both sides, the square root and the square are opposites. We would get x equals, and 9 squared is 81. So that's another way of doing this same problem. I prefer the first method, where I just kind of work from the beginning to end and I kind of just use logic and think through the problem. But there is this solving equation way that maybe you prefer. So I wanted to show both. Either way, x is 81. And then you could plug that in. If I would type this whole big ugly problem in, fraction 4 square root of 81 over 3 second caret 27. So I've typed this whole thing in, equals 12. I've now proven that my answer is correct because I checked my work. I plugged in my given value of x into the expression, and I got the right answer. Don't worry. Yours is not quite as difficult as that one. That one's a little hard, which is why we went through that together. Letter D. It says, at lunch, you counted your M&Ms and found you have 45 of them. You want to use all 45 of the M&Ms to make one of each different sized squares. So you're going to make different sized squares. What sizes of squares could you make and use all 45 M&Ms? So pause this video, maybe draw some pictures, try the problem. When you're ready to continue, hit play, and we'll go through it together. All right, so I'm just going to start listing off my perfect squares, numbers of M&Ms I could use to make a square. So I can make a square of 1. I know M&Ms aren't really square, but you get the idea. I could make a square using 4. I could make a square using 9. I could make a square using 16. That would be 4 on each side. I could make a square using 25. That would be 5 on each side. I could make a square of 36. That would be 6 on each side. I could not make a square of 7 on each side because that would be 49 M&Ms, and that's more than I even started with. So I can't do that one. So now you're just looking, let's say, which sets of numbers could equal 45. It says, what sizes of squares could you make and use all 45 M&Ms? So do you see any combinations of numbers here that add up to 45? I see one. I see at least, I can make a 6 by 6 square, 36, and this 3 by 3 square. 36 plus 9 is 45. So I can make a 6 by 6 and a 3 by 3 square. That's one possible answer. That uses all 45 M&Ms. Do you see any others? I don't know. I'm just kind of, I'm looking here. I'm just going to play with some numbers. Let's see. That's, oh, there's one. A 5 by 5, which is 25 M&Ms, and a, what did I have? Oh, a 2 by 2, which is 4 M&Ms, and a 4 by 4, which is 16 M&Ms, should be 45. It is. So that's another set of M&Ms you could use. It uses all 45 M&Ms. And there might be more out there. These are just the ones I can come up with here very quickly. Feel free to try some more patterns and see if there's any more, but these are the two I came up with. And it really came down to drawing a picture, recognizing that perfect squares, these numbers are called perfect squares make perfect squares of objects. Letter E. Philip was trying to figure out if the square root of a number is greater than or equal to the cube root of the same number. So just make sense of that first sentence already. So if I square root, say, 9, I want to know, is it going to be bigger, smaller, or the same as the cube root? Okay, that's kind of what he's getting at. Give an example with the square root of a number, or where the square root of the number is greater than the cube root. So this should be where. Give an example where the square root of a number is greater than the cube root, and also give an example when the square root of a number and the cube root, or the square root and cube root, have the same value. All right, so that's half of that is very easy. Half of that is a little bit trickier. So we want to find one example where the square root is bigger than the cube root. And that will happen almost always, if you pick any random number, square root of something versus the cube root of the same number, the square root's almost always going to be bigger. So if I pick, well, that 9 I had there a second ago, the square root of 9 is 3. The cube root, 3 second caret of 9, is less than 3, 2.08. So there's an example that fits the first scenario, where the square root of the number was bigger than the cube root. Now the second scenario is where the square root and the cube root were equal. This one you have to be a lot more strategic in your numbers, because most of the time they're going to fit into this first pattern. So a lot of times if you're trying to find little tricky patterns like this, it's good to think of numbers around 0. 0 and 1 are very common numbers that fit in a lot of different tricks that we don't really think about. Back in that the circumference example, I think it was the very first example of this lesson, I found that trick of, was it this one here? If I plugged in 0 for my radius, it actually made it a rational number. Now that's not really the intended part of the problem, but using numbers around 0 and 1 a lot of times can throw little monkey wrenches in your equations. So let's see if it works here. If I take the square root of 1 and the cube root of 1, are they equal? Square root of 1 is 1. Cube root of 1 is 1. So that actually works. And honestly, the square root of 0 and the cube root of 0 are also going to equal each other. So I gave 2 examples, but that's a good kind of mathematical rule. 0 and 1 mess up a lot of different equations, or throw little weird things in there. Something just keep track of in the back of your mind. If you ever have to give a counterexample, think about 0s and 1s. Letter F here. This is one for you to try. Explain in words why you can take the cube root of a negative number, but you cannot take the square root of a negative number. Example, if you try to take the square root of negative 64, it says domain error here, undefined. It just doesn't work. You literally can't do it. But if I do the cube root of a negative number, it works. I want you to play around with your calculator, or maybe write some stuff out and think about this. Why can't you take the square root of a negative number, but you're allowed to take the cube root? Pause the video, try it on your own. When you're ready to continue, hit play, and then we will go through it together. All right, so it comes down to the properties of square roots and cube roots. A square root is, you're trying to figure out what number times by itself gives you this, and that would be the square root. A cube root is what number times by itself 3 times gives you that value. This one has an answer of -4. We showed it on the calculator. It says so in the problem, because -4 times -4 times -4 is -64. -4 times -4 times -4 equals, what did I do? Oh, I used the minus sign because I was using my keyboard on my computer instead of the thingy. There we go. So -4 times -4 times -4 is -64. That has an answer. Cool beans. Now, this one. What is wrong with this one? Can you think of 2 numbers? Nope, I lied. Can you think of one number that if you multiply it by itself, you're going to get -64? And a lot of people think of like 8. 8 times 8 is 64. But 8 times 8 is not -64. And then they go, oh, yeah. You make them negative. -8 times -8 is not -64. -8 times negative 8 is a positive. Negative times negative is positive. So there's actually no way you can do this, which is why there is no answer. It is undefined. And you're not allowed to have just one negative like that, because now it's not a number multiplied by itself. These are two separate numbers. So the reason why this is undefined and where you can't do it is there's no way you can have a number multiplied by itself to give you a negative answer. Okay, that's what we're trying to like reverse square root this. We want to figure out what two numbers would multiply to give us negative 64, and there is none. There's never going to be an answer for that. It is mathematically impossible to take the square root of a negative number. Letter G says the expression square root of 81 has two possible solutions. What are these two solutions? Show why both solutions work. All right, well, if you square root 81, we get this. Now, this is something we've actually talked about a decent bit already over the past few lessons. You get the answer of 9. Do you remember what the other answer is? It's negative 9. Those are the two solutions. Now, show why they work. Well, because 9 times 9 is 81. So this number times by itself gives me that value. But negative 9 times negative 9 is also 81. A negative number times by itself is positive. So that also would be a solution for the square root of 81. They both work. Letter H says rectangle A has side lengths of 4 square roots of 8 and 6.4. Rectangle B has side lengths of 9 cube roots of 125 and square root of 64 over 6. Which rectangle has the greater area? I'd like you to pause this video. I'd like you to try it on your own. When you're ready to continue, hit play, and we'll go through it together. All right, so I'm going to draw my pictures. Rectangle A, rectangle B. I don't know which one's bigger. I'm just drawing two rectangles, and I don't know which side lengths are bigger. I'm just going to throw them in the picture. So I'm going to call this guy 4 square roots of 8, and this guy 6.4 repeated. 9 cube roots of 125, and square root of 64 over 6. Okay, I just need to label sides. Eventually, when it says which rectangle has the greater area, in my brain, I'm pulling out area is length times width. So I'm going to multiply these two values together to get the area of A. I'm going to multiply these two values together to get the area of B. I could theoretically right now just throw them straight into the calculator. Well, let's see. Area of this guy is 6.4 repeated times, or you can use parentheses, 4 square roots of 8. 6.4444444444444444444. Put a whole bunch of them in there. Times 4 square roots of 8 equals, my area is 72.91. Okay, cool. Other guy, area is square root of 64 over 6. I'm just writing small because I'm running out of space. Times by that 9 cube roots of 125. And actually, that one, you could almost do the whole thing in your head, but we can still calculate her. So we get square root of 64 over 6 out of this times 9 times the cube root. You had to do it the way I just did there a second ago. If you just did 9 3 second caret, it's going to make it a 93rd root, and you don't want that. You want 9 times the cube root. Oh, I already have the 9 there. Delete that thing. 3 second caret. So 9 times the cube root of 125 is 60. Which rectangle has the greater area? Well, it's rectangle A. And that was really just being able to type ugly things in the calculator. That's part of this skill as well. I know a lot of the lessons, or there was that one lesson on no calculator, but you should also be fluent with the calculator, being able to type ugly expressions in your calculator and get them correct. All right, letter I. Which two integers fall between negative negative square root of 36 over 3 and the cube root of negative 125? Vocabulary word. Integers are numbers like 2, 5, negative 9, 0, negative 8, negative 13, 7. They are no decimals or fractions. They're whole numbers, but they're allowed to be positive and negative. Okay, so I'm looking for positive and negative whole numbers that are between these two numbers. So I should probably figure out what these numbers are first, and then I can come up with the two integers between them. So I'm going to simplify. Now, I'm actually going to do this one without the calculator because these numbers are numbers that we had in our chart from previous lesson. This 36 is a perfect square, so I can square root it perfectly. This cube root is a perfect cube, so I can cube root it perfectly. So I'm going to do, let's do this first one first. So I'm just going to rewrite the problem. All right, I know the square root of 36 is exactly 6. That is a perfect square. 6 times 6 is 36. And then when I simplify this expression, I get negative 2. That's one of my integers. Here, the cube root of negative 125 is negative 5. 125 is a perfect cube. The cube root of 125 is 5, but because of the negative, we get a negative. All right, so we simplified. Now we just got to figure out what two integers are between negative 2 and negative 5. And hopefully in your head you're going, negative 3 and negative 4? Yep, yes they are. Those are the two between negative 2 and negative 5. That's it. Letter J. Daniel needs to match up each rational number with its decimal equivalency. Help Daniel by drawing lines from each rational number to its decimal expansion. So we need to match up numbers on the left and numbers on the right. I'm looking for if there's any that I recognize. I do recognize, well, actually, no. I'm not going to do this first. You're going to do this one first. Pause the video. Try this one on your own first. See if you can match up left and right. When you're ready to continue, hit play, and then we will go through this together. All right. Now, as I was going to say, I recognize these two are going to go together. I recognize this over 9 means that this is going to be a repeating decimal. Out of these, this is the only repeating decimal. So I knew that one was going to be a thing. Other things I know. I know the fraction 1/4 is 0.25. So those two are a pair. Out of these last two, I'm looking at this 8.125 or 8 square roots of 25. Square root of 25 is a perfect square. That's 5. This is just 8 times 5. If I would simplify, so 8 times 5 is 40, which leaves this. And you could have easily done that on your calculator. If you even just put in 0.125 and hit your switcheroo button, and then simplify it a whole bunch. There we go. It does simplify down to 1/8. The other option, probably quicker, would have been convert the 1/8 to a decimal by dividing, and you get that decimal point. All right, I think we are on the last question. It's a multiple choice. It says, a square has an area of 50 centimeters squared. That's an ugly square. You know, let me try that again. Closer. Area is 50 centimeters squared. What would be the perimeter of this square? Round your answer to the nearest thousandths. Okay, interesting question. So we have the area, and we need to find the perimeter. The connection between area and perimeter is the side lengths. I know that area, because this is a square, it's going to be side times side. And I know that perimeter, to find the perimeter of any shape, you add up all the sides. So top plus bottom plus left plus right, it's going to be side plus side plus side plus side, or if you like it better, 4 times the side length. So the connection between these two things, between the area and the perimeter, is the side length. How big is each side? If I knew that, this problem becomes very simple. But that's the actual thing they're trying to, well, the hidden question in this problem is, how big is each side of this square? So we're going to work at our area, because that's the only one we have any numbers in. I know that the area is 50. Can you think of two numbers? If you multiply it together, you get exactly 50. What number times by itself is 50? So you can't say 5 times 10, because that's not a number multiplied by itself. You can't. It's an irrational number. It doesn't work out exactly. It's a little bit bigger than 7, but not quite 8. The way we would figure this out is we can square root 50. If I square root 50, this tells me what number times by itself gives me this. What number times by itself gives me 50? Well, it is 7.07 on all sides. And I guess I should probably keep the 1 since we're supposed to round to the nearest thousandths. If you said the answer is letter B, you are wrong. It is not letter B. That is not the answer to the question. That is how big each side is. That is not the perimeter of this square. The perimeter of the square we would find by adding up all 4 sides of this. Now we know how big one side is, 7.071. I'm going to multiply that by 4. That's the same thing as adding itself to itself 4 times. And we get letter C for an answer. This 12.5, that's for students who they try to take 50 and divide by 4. And you would think that that's the side length, the length of each side, but it's not, because 12.5 times 12.5 does not equal 50. Okay, so dividing by 4 does not do what you think it's doing. And then 50 would be what happens if you thought this was the side length and you multiplied by 4 and you get that as the perimeter, and those just don't work. So letter C is the correct answer, and hopefully that was a good explanation on why. And for our summary, since this is the last lesson on rational and irrational numbers, can you list 3 things you learned about rational and irrational numbers? So you might have put down things like rational numbers can be turned into a fraction. Irrational numbers are decimals that do not stop and do not have a repeating pattern. They go on forever. We usually think of irrational numbers as big, ugly decimals, where rational numbers are usually short, pretty decimals. Not always, but usually. Something like 3/17 we saw, even though it is a rational number, its decimals are very, very ugly. It's just because it goes on past what the calculator can show us, but we know it's a rational number because it starts as a fraction. You could say how you learned how to compare rational numbers by changing them into, or comparing rational and irrational numbers by changing them all into decimals and then figuring out which ones are bigger and smaller. We learned how to put them on a number line. We learned how to estimate square roots, how to estimate irrational numbers using perfect squares in our charts and tables. You learned what a cube root is and how to estimate cube roots, which could be both rational and irrational. So there's lots of things you could have listed here. I can't even list all the things you could have learned. So I'm going to do a quick little recap of the whole lesson, and then we are going to be done. So starting at the tippy top, we learned to be cautious with pi again. You can't always just use pi as the number 3.14, especially if you're looking at the difference between a rational and an irrational number. You have to use the whole pi, all of those digits, if you're trying to figure out rational versus irrational. If you were just asked to find the area of a circle or the circumference of a circle, then 3.14 is usually good enough. We looked at the difference between squares and cubes and the formulas that we can use. Squares is area equals side squared, where a cube, the volume is calculated by doing the volume equals the side length cubed. And we found out you can square root the squares to figure out how big each side is, and you can cube root the cubed to figure out how big each side length is. We did two different methods of solving this problem, where one we worked from kind of beginning to end, and we worked front to back, and we calculated in the middle that our x value should be 81, and another method where we kind of solved an equation, and I have the equation method still here. We still found the x value was 81. We looked at drawing pictures to help us understand what dimensions, what number of objects make a square, and these numbers are called perfect squares. We learned that square roots almost always give you a bigger number than a cube root, but there are some exceptions, especially with numbers like 0 and 1. We learned why you cannot take the square root of a negative number, because there's no two numbers that multiply together that will ever give you a negative solution. We refreshed our knowledge on why the square root of a number has both a positive and a negative answer. This problem was basically learning that we can type in big, ugly messes of problems in our calculators, and we should be able to do it fluently. Feel free to practice again being able to type something like that in the calculator, and if you forgot how to do that already, rewind the video and watch that part again. We remembered or learned what an integer is. They're positive and negative whole numbers. We did a little bit of matching. There's really nothing new in this problem, but being able to convert our fractions to decimals and back. And then this is very similar to the one square question up above, knowing that if you square root the area of a square, you will get its side lengths, and then being able to convert that into a perimeter by adding all the sides together. So this has been this lesson. Thank you very much for watching. Until next time, toodles.